So this last section of astrophysics, we're going to talk about black holes, orbital velocity, escape velocity, event horizons, kind of like, you know, like how gravity acts on these large-scale objects like black holes and galaxies and things like that. So let's start off with what a black hole is. A black hole is basically a star that was so massive that it basically just got so much gravity that it got so dense that nothing can escape it, not even light, because in order to escape a black hole, you need to travel faster than the speed of light, which is impossible. So what a black hole does, one visual of a black hole is talk about gravity wells. A gravity well is a visual that shows you like the deeper the well is, the harder it is to get out of the well. So a black hole, this is a black hole, it's curving the well, space and time. So in order to get out of this well, I need to, let's say there's like a marble here. If I take this marble and it's going to fall towards a black hole, I need to give that marble enough energy to leave the pole of the black hole, otherwise it's going to fall back in. So let's derive an equation for the event horizon. So here's the definition of the event horizon. It's literally like the distance away from a black hole that nothing can escape. Meaning if you get closer to than this distance, you're in trouble because there's no possible way for you to escape that event horizon. So here's how it works. It's all based on conservation of energy. So for that marble, if it falls within this well, it can't get out. It just doesn't have enough energy to get out. So one way to think of it is when the marble is trying to leave this, it has kinetic energy, which is 1/2 mv squared. When the marble gets to the top, it has potential energy, but we don't use mgh because that's on Earth. We're by a black hole, so we need to set it equal to universal potential energy, which is this. Now, a bunch of stuff in this equation cancel out. We have the mass of the marble cancels out, or the mass of whatever it is. G, if you remember, is a gravitational constant. 6.67 times 10 to the minus 11th. That's universal gravitational constant. R would be the event horizon. It'd be like the distance away from the black hole that you could potentially get before you can't escape it anymore. M is the mass of the black hole, and V would be the velocity that you need to travel to escape the black hole. Now, let's actually rearrange this for V. V is going to equal, well, let's actually rearrange this for R. R, I multiply both the other side by R, then multiply the other side by 2, and divide by V squared. So that's going to be my event horizon. It's going to depend on the mass of the black hole. The more massive it is, the bigger it is, the bigger the horizon is. I mean, the closer I get to it, like I can be farther away from it and still can't escape it. What would V be for event horizon? Well, the fastest that I can possibly travel is 3 times 10 to the 8th meters per second. That's the speed of light. So even light can't escape it because it can't jump faster than the speed of light. So that's how you can figure it out. Another thing we can figure out, so I'm not going to do an example, because we can make a massive, we can make up any mass we want to, but that's how we figure it out. Another thing we can figure out is like how fast are like objects moving around in a galaxy. So the center of a galaxy is a black hole. There's so much gravity that things are kind of slowly getting sucked into this black hole, so it's spiraling in. And as they get closer to the event horizon, then they can't escape. Where does it go? I don't know. It just adds to the black hole. So this is a galaxy, some unknown galaxy. And we're kind of right here in this galaxy, the Milky Way, for example. We're kind of going around in this circle, slowly spiraling into this black hole. So we're going to use a combination of equations here to try to come up with an equation that relates everything together, like how does the velocity of the black hole, velocity of us, change with distance and density and all these things. So here's some equations. So density of anything is mass over volume. Now, so you can think of like the this region of space as spherical, even though it's not. We're going to assume it's spherical. So the volume is 4/3 pi r cubed for a sphere. So I can put that in right away. Density is mass over 4/3 pi r cubed. Now, I want to come up with an equation that relates velocity and density, not volume and density. So here's my force equation. I'm going around in this circle because of gravity. Gravity's pulling me towards the center of the circle into a black hole. And it's centrifugal force that causes me to go in orbit. Centrifugal force equals gravity. So remember the equation for centrifugal force was mv squared over r. Equation for gravity, gmm over r squared. The mass cancels out. And one of the radiuses cancels out. So v squared equals gm over r. Now, what about this mass that we're left with? We can replace that mass with density and radius. So I'm actually going to solve for mass up here. Mass is equal to density times 4/3 pi r cubed. So I can replace mass with density times 4/3 pi r cubed. Density 4/3 pi r cubed. And the 3 can go on the bottom. One of these r's cancels out, r cubed on top, r on the bottom. So it's r squared. So let's write it up here to see it in a little bit nicer form here. So v squared equals g density 4 pi r squared over 3. I'm going to square root both sides. So square root this side, I got to square root this side. Now, the square root of r squared is just the same thing as saying, if I can pull it out, multiply by r. So this is one of the equations in your phone packet, and that's where it comes from. It's basically a relationship between those variables: density, mass, velocity, radius. So it's basically an equation that relates concepts of like velocity, of how fast you're moving around this galaxy, the size of the galaxy, such as the radius. There's a couple of constants in here, and the density of the galaxy. You can use this, like you can actually rearrange this equation for density and figure out what is the density of the galaxy, or of space itself, if you knew your velocity. What's another way to find velocity? Well, you remember back to circular motion, velocity is 2 pi rf. You can also use that to figure out velocity. How do we figure some of this stuff out? How do you find frequency? Well, how long does it take to go around this galaxy? You can use the stars to kind of indicate, like, well, I noticed that star, and keep track of that over time. Radiuses, we use parallax and things like that to figure out radiuses. So it's actually very clever how, over the decades and centuries of studying astronomy and the stars, how much we've learned. And that's why we got to keep it going, because we find out more and more about this stuff. But if we lose that information, then we got to start over. It's kind of like we got to keep that information going. That's why it's important to keep studying this stuff and communicate with scientists and keep good detailed records and further your investigation and better your experiments along the way. So basically, the last section here is just to kind of derive some equations for you that you can use to kind of understand like how velocity ties in with black holes and galaxies and how all those work together. So there you go. Astrophysics complete.